and then share screen. Guess that's the screen. Then is it recording this thing now, or what's doing? This is just the video. This will be my normal camera, and it's recording this. I think it's okay. I will take you through my mental eliminations here. All right, there. So this paper, we went through already the paper anyway. This guy. Did you guys get that email about the talk? There was a talk. We're interviewing people for faculty for materials. You know, a guy came from. He was at Brookhaven National Lab. Now he's in British Columbia, but he's doing these bottle brush polymers, you know, which are. This is the other thing that's this guy. I should definitely get here half an hour before the class. That guy's there. Go to .cam. I think that projects into the Zoom then. I'm hoping. But anyway, bottle brush polymers are these polymers that have, so you have a linear chain, and then you can put side groups on it like that. And if you put enough of them, we call it a bottle brush, because it kind of looks like the thing. I guess those test tube brushes is what I always think of, that have like a thing like that on the end. So it kind of looks like that. Or it could look like a pipe cleaner, actually, but they call it a bottle brush. Anyway, he's working with those, but he makes a block copolymer. So he has like the A part and the B part. And the A part is polyethylene oxide, so it's CH2CH2O. So if it's just that, it would be polyethylene. When you put an O on it, makes it hydrophilic, so that dissolves in water. All right, so that's part of a group of pluronics. The kind of polymers that are made of polyethylene oxide, also called it's like glycol. What do you call that? Polyglycol or something? Polyethylene glycol, yeah. Okay, thanks. The other part would be PPO for the pluronics, which isn't water soluble. Right, so it's got a methyl, it's the same group but with a methyl on the side. So it's like polypropylene oxide. Anyway, those black copolymers separate out when you put them into water. So you make it makes kind of like a polymeric surfactant that you can use for drug delivery and things. Anyway, so he's doing that, and he puts inorganics into the PEO part of the blocks, and then he kind of wants to make some kind of sure what he was making actually. He's making these things will separate into sheets. So he has like silica or alumina layers, you know, and then they make, because it's like the polymer size and making nanoscale. It's kind of an interesting talk. I think you might enjoy listening to it, but it's an hour, you know, so there's no credit or anything for it. Anyway, if you want credit, you can get credit, but we'd have to figure out how to do that. Anyway, so this paper, this is about rings and linears, and that's also like a long-standing thing in polymers. So basically, the ring thing, they've been around for a while because like silicon sealant, there's a natural equilibrium between the linear chains and the ring chains. So that whenever you have silicon sealant, there's a bunch of rings in it. So you can separate out the rings from the linear because the rings are shorter. They generally have a lower viscosity. Right, so you can separate the two and get just rings if you want. All right, so he's doing this, but he's doing it with I think he's using polystyrene for this. So anyway, so basically there's a difference in the two. And he says in the beginning that these things collapse, like the rings collapse, which is only partly true. So there's a story to the collapse thing that we'll talk about later. But basically, because they have less entropy. So entropy is what makes things dissolve. Right? In other words, randomizing. So you have enthalpy tends to make things come together and come out of solution. The randomness makes it want to go into solution. That's why when you heat it up, it goes into solution. But because this thing's tied together, it's got a lot less entropy than the linear one. So it could collapse down, depending on how the situation is. There's some entropy in it. There's less than there is in a linear chain. So he says right at the beginning, well, they're collapsed, which it isn't necessarily true. Like he says that, but it isn't really true because there's can be a transition. Anyway, so but the picture he shows isn't really collapsed. It's like this kind of linear structure. So it's not. It wouldn't be collapse. Would be like a 3D blob, just a single chunk of stuff, right? So, anyways, that's kind of the thing. You guys looked at it already, and let's see. So first thing is like this G prime, G double prime. So everybody got that pretty much. I mean, a little bit like some of the or one group like kind of copied the something from somewhere and spit out like what the machine is. And that's not really what I'm looking for, but it didn't matter. Basically, whenever someone says like, what's this machine? And you have to think like, I'm going to build it. Like, how would I build this machine? It isn't like, what is it? Like you go to Wikipedia and copy it. It's like, I'm going to go to my garage. I'm going to make one of these. And what do I need? First, you want to make a list of like what you need to do it. Right, so you're going to say like, I need some torque meter because I'm going to be spinning the thing. I'm going to need it like something to measure the speed, like frequency, torque. And then I'm going to have this geometry. Like I like this cone geometry because you get constant shear rate. Oh, all right. Yeah, this is like going to take a while to get used to. I may never get used to it. So you have that because the gap, the gap width, the gap thickness kind of goes with the radial position. And also the speed around this, because the circumference goes with the radial position. So your kind of your angular velocity goes with radial position. And the shear rate is going to be like the strain, like the rate of strain. That's going to be like the distance in the vertical direction versus the distance in the horizontal. So it's because of shear. So anyway, that's going to go with R over R, and this cancels, so you get constant shear rate from it. Right. So that's the best geometry to use, especially if you have a fluid where you know that the viscosity has like a dramatic dependence on shear rate. So if you put this fluid, say, in a pipe, it's a normal Newtonian fluid. So you get no shear in the middle and a lot of shear at the side, right? So you get this kind of parabolic flow profile. If the shear thins, and at the high shear, that guy speeds up, and at the low shear, it slows down, so you get plug flow. So polymer is always going to be plug flow. Right? It gets into a pipe, a tube or a die or something, right? So you're not going to get a parabolic profile. Anyway, so something like that. But then there's two ways to run this. One is just let it spin continuously, and you're going to get like gamma dot. That's how you do the viscosity measurement, right? That thing where you get that curve, right? The other way to do it is to oscillate this thing and get the complex parts. So you get the in phase and out of phase. If you're just going continuously, you just have like one number. But if you oscillate it, then the strain is going to go sinusoidal, and the stress will be offset from that. Right? So you have this phase shift del, and then you can plot. People will talk tan del, like tan of the phase shift versus frequency. You find out that del like reaches a maximum at a certain frequency, right, for a certain time. So 1 over time is the frequency. So there's this magic time, and that tan del reaches a maximum. That's when the material is like sucking up as much energy as it possibly can get. Tan del is going to equal G double prime over G prime. If you write out that G star is like G prime times sine del and then omega whatever plus cosine G double prime, imagine it. So if you do that, you can figure out that the tangent of the del, because sine over cosine is tangent, and you end up that G double prime over G prime is tan del. So anyway, the peak of that is where you have the maximum loss. It's where the material is absorbing most energy. That's its natural time. That's the time that it wants to just, you're shaking it and it's going right with it. Like you rang the bell, that's the tone that the bell makes, right? So your polymer is like a bell. You found the frequency, the natural frequency for it. Anyway, so something like that, you know, there's a lot to it, but anyway, somehow think about building the machine. Any machine question is always going to be like, build the machine. How do you build it? You know, what parts do you need? Then the temperature control will be really important because viscosity is going to be exponential in temperature. It's going to follow Arrhenius dependence, right? So you're going to have, so you have to have like some kind of temperature control on this. Like, you're going to have exponential, some activation energy over KT, which means that your viscosity is going to go like that in temperature. But it's going to have like a steep dive. So some zero viscosity. So anyway, you then need to have temperature control on it too. Oops, let's show the right thing. All right. That's good. All right, so anyway, that's that business. Then we went through these two numbers. Everyone got that. Everyone got everything in here, really. The part E, one group did really well on part E. I don't have it here, but it seemed like pretty impressive. First off, they disagreed, which I agreed with them, so that helps. But his explanation seemed to be pretty bogus. Like this idea that they're going to form this this thing that's hard to even like draw, right? Like I know what it is, but it's really hard. I went to draw it and I had a hard time like drawing what this thing is. So you have like when you, it's also called like they do it for horses, right? You loop the rope around, like when you try to tie your horse to a post and you have like the line there, the horse is over here, right? It's chicken, but and then like somehow you get the thing so it loops on it. See, I can't draw it somehow. Anyway, you get the loop to lock on itself. Somehow it's kind of not, right? And you can say like, I mean, you can imagine these things are tumbling around and some of them loop into each other. And then the two ends would pull and then it could make something. But in order to actually increase the torque, the tension on that, you'd have to have like a lot of those. Like it would need to make a connection that would go all the way through. That was what that group said. That's true. Like if making one of those is like, say, 1 in 100, then making 2 of them, and then you're going to say like you need to have like 100 of them, right? So it's not going to happen, right? So like if probability is low to make 1 of those, to make a network of them is like seems not possible. They came up with some other reasoning for it that seemed to be pretty good. I don't know which. Anyone want to say anything on that from that group? Or some people just said, yeah, that's okay. I like the cow and that thing. That's all right. I mean, it's open-ended. So anyway, so when it goes into tensile flow, right, then it all of a sudden it thickens instead of thins.
But why do you think that is?
I don't know. I really don't know. Like, I mean, it could burn or something. It could break the chain. I don't know. It could be, I think it could really be experimental. That's a really difficult measurement to do.
Is it
Extensional flow.
Is it also appeared in linear polymers or just ring polymers?
No, only the rings. So yeah, all right. The cow thing would happen with linear too. That's the other problem. I think that group mentioned that. The cow thing is not exclusive to rings. Right. I mean, it's maybe harder to do with linear, but the whole cow thing is kind of interesting, I guess. The whole fact that it sure thickens on an extensional flow. And the way they do it, like to study it, they'll have like this kind of setup. Because extensional flow, you get an exponential reduction in the size of the thing as you pull it. So experimentally, you need to have an experiment, like in a normal tensile, you just go at a constant rate. Or to get constant tension flow, you have to exponentially increase the rate of pulling it. It's not really possible to do, right? It's like really hard to do. To get around that, they'll do this kind of T-shaped flow apparatus where you flow in and then out, and then exactly at that spot you get perfect tension, extensional flow. Right, so you need to have picture like you do as polymer melt. It needs to be like an extruder. So you have to have two extruders to somehow make it split stream. Then you can only study the tension here. So somehow if you get the viscosity at that spot, it's not easy. So it's kind of crazy. So the viscometer companies have been spending a lot of time manufacturing extensional flow because it's important to fiber manufacture and films and different kind of polymer situations. So everyone's interested in it, but it's still not easy to get that. Anyway, so that's kind of that business. I don't know, any other comments on that stuff? I thought it was kind of an interesting paper, and it was recent and had something to do with at least that flow, the rheometer.
I got a quick question.
Yeah.
For loss and storage modules, it's a log log plot, it's linearly related with frequency, right? Or the total flow.
So
The viscosity doesn't change in that flat region in the low frequency areas.
Are
The
you
loss
talking-
and storage modulus or log plot with frequency are going to be a straight line in that same region, right?
all right, so the G double prime goes up with the power of 2.
Right.
G prime goes up with the power of 1. And they cross over, that's at your tau. That's the time where that's at the peak in the tan delta kind
That's
of
the
thing.
transition from Newtonian to non. Right. That's what the whole.
No.
model is, right?
Oh yeah, all right, it is. You're right. This part is Newtonian flow, the power 1, power 2.
Yeah.
And then in this plot, the storage modulus like plateaus out, right?
Yeah.
And at that point, that's called the plateau modulus G0, and that's going to be proportional to 3 RT over the entanglement molecular weight. So it acts just like an ideal rubber. Like we got last time, we had exponential minus R squared, 3, 2, and L squared, and we had exponential of some energy of R over KT. This is a Gaussian chain probability for the ends. That's like your probability for the ends versus R is a bell-shaped curve. So it's more likely to have the ends at the same spot. Oops. You're more likely to have the ends at the same spot than far apart. And the maximum they can go is the contour length, right? And then this is just the thermally activated process, Boltzmann. In other words, there's an energy of activation, it has to overcome that to have the thing happen. So you equate those two, you get the energy of the chain is KT times 3 KT R squared over 2 and L squared. And if you apply a force to the chain, and you want to get the force is going to be dE dR. To take the derivative of that thing, you get the 2 cancels, 3 KT over NL times R. So that's your 3 RT over ME. That's your molecular weight. That's your rubber. That's called rubber elasticity. So in the time scale, when you're shorter times and when the chains can relax, then your modulus follows rubber elasticity. It's as if the entanglements are permanent, just like if it was a rubber, like they have cross lengths is stuck there. When you go below that time, so when you go to longer times above that time, then it can flow. So it's a different way to look at it than the other one. Like the other one would be like the viscosity, so it's just flowing. So they're the same time. That's the point. Like the Cox-Mertz thing is that those two are the same time. The same thing is happening. So yeah, that transition happens. So essentially, that's what you're asking, right?
Yeah.
So those are the same thing. Like, and it's because the viscosity is going to be like the frequency times the loss. So that'll end up giving you that this thing's a flat thing, because this power one becomes, so if this is, somehow that works out, so that becomes a constant. Right, and then it makes it decay when you get over here. Right, so, but the complexity of this is that they're entangled, so you don't know the details of that. So that slope, it's 0.58 for the rings and 0.87 for the linear. And kind of by this would be 1, I guess, -1. So whatever it is, like there's some details, there's a rough feeling for what's going on, and there's the details. Right? So anyway, hopefully that's kind of, it's a lot of stuff, but again, like there's so much stuff that just have the dump truck dump the garbage and then pick out the parts that are important. And then, all right, some of it you'll not get, but you need the parts that people are talking about today. Like you need to understand what people are talking about today, not like 50 years ago, right? So looking at papers is a way to go.
Kind of a random question
Yeah.
about the rheological measurements.
Yeah.
So I understand when they're constructing master curve for the material, the time temperature superposition vertical shifts, but then they're talking about the WLF horizontal shifts.
Yeah.
Can you briefly touch on how they're, I know it's a Fourier transform to get to the master curve, but can you briefly touch on how they're doing the horizontal shifts, the William?
Yeah.
out there?
Yeah. Let's see, dock camera. Right. So it's not that difficult. I mean, WLF makes it look difficult, right? It's the same function. It's this exponential. So viscosity is like time. Okay, it's kind of like shorter relaxation time means you have a lower viscosity. Right? So they're kind of the same thing. Anyway, and then you have this exponential minus EA over KT, right? So you have time and temperature. So they're related by this exponential. It's gonna be like log of time. So time by T0, some reference time, and that's going to be related to the energy over like KT. So you can convert like the temperature scale to the time scale, right? It's just this thing. Okay, now if you want to make that more complicated, there's 2 ways that you'll do that. WLF complicates it in 2 ways. Okay, one is this is absolute temperature in Kelvin, right? So your reference temperature is 0 degrees K. But if you have a polymer, it's got a glass transition and motion stops there essentially. The motion you're interested in stops. Like motion at really small scale doesn't stop. So there is like heat capacity and things to it. But basically the kind of thing you're interested in, the flow stops at TG. So it means it isn't referenced at 0. You should have a Vogel temperature that references it. See, that's one parameter, the add in, right? The other thing is that in the original, you're saying that this isn't temperature dependent, but the energy is actually the enthalpy. So say this is the energy of the barrier, it's the enthalpy minus delta S, right? So that's the real Gibbs energy that you're talking about. That means you have another parameter, like some kind of parameter here. So you have 1, 2, 3 parameters. And WLF is a 3 parameter. So you can work out, if you work out the Boltzmann, that it's minus delta H plus T delta S divided by K times T minus T Vogel, then you can work out the WLFs. I think they're like A, B, C or something, constants. It isn't delta S and TV, but they're functions of those. So it's like 3 parameters you add in. So it would be nice if they had just written it that way. Then you could say like, that's what that thing is. But instead they did it empirically and they found out the same thing. They found out that it can be, but if you're far from TG, in Kelvin, you can forget about this number. And basically, you can kind of forget about the entropy. In most cases, you can just do a one parameter fit, and it's just as good. Like we did this in the lab for siloxanes. And there's no difference between a WLF and an Arrhenius. It's just two more parameters. Right, so if you're far from TG, the Arrhenius function, I don't know how to spell it, but his function is just as good. So there's a relation between time and temperature. That's kind of the end point of it. So if you do your frequency sweep, because it's mechanical, there's only like a couple decades you could get. But what you need to do that whole spectrum is a lot of decades, like as many as you can get, in fact, so you get two crossovers. So basically you do a different temperature runs and combine them together. It works okay if it's just one material, but things aren't usually just one material. So you take like a tire, you want to do a WLF for a tire. Well, it's got carbon black, 60% carbon black, then 20% silica, a little bit of rubber. There's a huge amount of oil, right? In fact, it's like 40% oil. I got my percentages. It's usually in parts per 100 rubber. So it's 40 parts per 100 oil. And then it's like 80 parts per 100 carbon black. And then they'll put in silica. So you have this material that you have, it's just a chunk of rubber. You want to do a dynamic mechanical to see how because different frequencies will relate to how it does different things like cornering and wear when it's wet, like how does it grip the road. Different frequencies are going to affect that, at different temperatures. So basically you want to know, it's more complicated than just the one number. But people will ignore that and just use the one number. And the other thing is, like you're saying X and Y axis, so that's the time axis, right? But the other axis also has a shift factor that's kind of like a fudge factor. So you need to do something to the other axis to make it work. And people just, there's some analytic thing to that other factor, but any paper that you read, I think in this paper, even if you read it, he says like, then we just shifted the other axis. Right. I mean, he says that, everyone says that because that's what you do. And you can get it to look pretty good until it looks good. That's what I think he says, almost says exactly that. And no one says like, that's not exactly science, But basically that's how it's done. Yeah.
Shifted so it looked right.
Yeah, I mean, you can tell when it's right. I mean, the curves line up. So you have the two curves will be on top of each other. Why it does that isn't exactly that clear. I mean, there's some shift that you can calculate, but that isn't the number you get. And once you get beyond, anyway, the system's also Pauli disperse. So even if it was just polymer, it's not just polymer because it's polymer of different lengths. And there might be some other stuff in it too. So you can't filter. The thing about polymers is you can't filter it out because the thing you're trying to filter out is the same size as a chain. So it's not possible to filter it even if you put it in solution. So anyway, there's a little bit of guesswork on the y-axis of this thing, but the x-axis is pretty solid. Yeah, so that's about it, I guess, on that. It's good to do the experiment because it's not believable that this would work. I mean, then you can put this into a simple, like a Couette viscometer. It's coning, it's a bob and a cup kind of viscometer, and just spin it and measure the torque. You can do that at different temperatures, and it works perfectly well. So it's kind of like surprising to see, but anyway. So it's an interesting theory, and it also kind of works. So it's nice. Did I download the PDF thing?
Yeah, if you click on down at the bottom of your screen, it says slides one on the left.
Oh, that's all right. Oh, that worked. Good. All right, thanks. Good. All right. So I hope that I can just use this guy. So I went through this. This is kind of, I think it's worth going through just because it's Einstein. It's one of his most famous papers. So it's kind of went through that last time. It's pretty simple, considering it's Einstein. It's just two, so this idea of Taylor series, you have some number is dependent on two different things. So you hold one of the things and then you do an expansion on the other. So you do the derivatives, like the thing, and then the derivative and the second derivative, third. And the prefactor to that, and so you can explain anything this way, right? This is common, like how you explain everything. So this is like the first rule of how you explain things. Then you do the same thing in time and in space, right? And then you find out, well, the integral of the Gaussian, if it's Gaussian, or any, even a symmetric function, any symmetric function. So if it's moving in space, forward, backward, that integral is going to be 0, going to be 1, right? I mean, let's see, this integral goes to 1. The probability integral, the integration of it is 1. And when it has the direction in it, since the direction goes plus minus equally, that goes to 0. So because space is in two directions and time is in one direction, that's why you end up with this business of the linear equals the square, the second derivative, right? And then when you solve that, you get the exponential. Oops, you get this thing. So, oops, not that thing. You get this thing, which is the diffusion function. Like if you start with stuff at some place 0, and you wait owing to time, it's going to go to a Gaussian. And again, it's Gaussian, so it's equal. Space, the argument has to be squared. So that's the lowest order that you could talk about something that's equally spaced. And then this is the standard deviation, or the variance, the square of the standard deviation, 2 sigma squared down here. So that means that this x squared is going to be 2 dt. So that means this is an object that the position of it goes with the square root of time. So you'll see that over and over again. So even in that talk, like the guy talked about motion of these bottle brush polymers, and he's plotting like, what does he plot? He's plotting, so you plot the,
You want to turn on that?
yeah, I'm trying to think too at the same time. It's like, what does he plot? He plots the correlation function for position, right? So you're at one position at time 0, and you're at another position at time t. You find like the overall average of that. So if you're here, what's the probability it went over here or over there? Then do that for every position in space and sum those up. It gives you this probability function. So you get that thing versus the time that you waited to look. And that thing will decay. So if time is 0, they're at the same point, and then it'll decay down, right? That's a time correlation function. So anyway, this thing will go with time to the 1/2. You'll see this time to the 1/2 term in it. So basically that means that it's diffusion, right? And then he also sees in the same talk, he sees that decay go with time to the 1, which means it's ballistic. And he says ballistic in the talk too, verifying that ballistic is a word that people use today, right? So anyway, it might be worth looking at that talk. So anyway, so that's kind of just, so the thing is used like all over the place, right? This kind of idea, even though it's from 1905. So it's kind of the basis of understanding a lot of things. And then in this anyway, this is the this gives you the Stokes-Einstein equation for the diffusion coefficient, which is an odd thing. So the reason it's odd, so in the paper, he doesn't bring out that it's odd, but it came out later on that this is really kind of odd because viscosity is a bulk property, right? Viscosity you can measure in your garage, like you can build the viscometer and measure the viscosity. The hydrodynamic radius is a nanoscale feature. So it's like quantum size. Right, and temperature is also kind of nanoscale. The diffusion coefficient is nanoscale, right? So it's relating a bulk number to a nanoscale number, right? And that's brought up a lot of people have talked about that. This equation is odd because you're relating like something that shouldn't be related to each other. Some kind of average system number, like these nanoscale numbers, right? So nano or even molecular scale. This can be atomic scale. So anyway, so that, that's why it was like an important thing at the time. It was relating the two things that shouldn't necessarily be related. Is that business. Then we went through this thing about, that I just did again, you know, that you can say it's got this Boltzmann temperature distribution, and you can relate it back to this Gaussian. You can write the energy for a chain, which turns out to be useful because you can get this rubber elasticity law from it. And then the other thing the Gaussian can give you is these moments. So we talked about that. Then I went through how to do the derivatives to get the average R squared, and that R squared is going to be in the end, we knew it was NL squared, so we can say sigma squared is NL squared, basically. And then that gives us the function for the Gaussian, for the chain. And then we went through dimensionality stuff. Let's see. So anyway, yeah, the dimensionality stuff, I need to talk more about that. So then that brings us to this thing about short range and long range interactions, right? So let's see. So basically you have this chain. It's a Gaussian. I mean, I showed you can make many different ways. So if you think about it, like this can't happen, like it can't cross itself. Okay, so Paul Flory, I think he died in like 72. Paul Flory he went to Ohio State and he got a PhD in physical chemistry. Then he came to UC and taught chemistry department. And then he was recruited from UC to go to DuPont to work with a guy named Carruthers, who invented nylon, invented all the polyesters and condensation polymers. Right. And then so Carruthers would have won a Nobel Prize, but he killed himself by making his own cyanide. So don't become a chemist. Flory, on the other hand, lived a long and illustrious career. So he's kind of a physical chemist. So anyway, so Flory did all the theory. Carruthers needed someone to do the theories for polymers, so he hired him. And then Flory stayed at DuPont for a while. Then he went to Goodyear. And then he did, during the war, to develop rubber. Then he went to Cornell, won the Nobel Prize, went to Stanford, cashed it in. So, warmer at Stanford. Like right now, today, upstate New York is -20. So in Stanford, it's 60, 65. You know? So basically, he wanted to go to a warm place. Anyway, so this thing Flory called long-range interaction. So you got, it's called long range because you have the index of the chain, you have 0, 1, 2, 3, 4. Then you get up to you don't know what it is. And then you're at some position. So that's I and J. So I minus J is some big number that you don't even know how big it is. So you've forgotten where you are, then you have an interaction. That's called long range interaction. So he means long range in terms of chain index, not in terms of distance, because all interactions are going to be short range. The only interactions that you have are short range interactions. Okay, so I mean over kind of 10 angstrom scale. Right. So but it's a long range interaction because chain index. So we'll deal with that later. That has an effect. But and the other kind of interaction he had was called short range. So he came up with these two terms, a coil expansion factor, and then the C infinity, Flory did, to talk about these two things. Short range means that I'm at 1, and then the next one is at 2, and they have an interaction with each other, right? Because they're next to each other. So that kind of interaction would be like, well, I have a bond, carbon-carbon bond, and then this thing can rotate about that bond, right? So there's this bond angle restriction, and there's this rotational restriction. And then if I start adding side groups on it, like if I have an OH group and I have kind of a negative charge, the charge interactions, those kind of things will be like short range interactions. They stiffen the chain up. Right. So you have this, you have some length that you have for the monomer, right? And then there's a length that the chain chooses. There's another length scale that the chain chooses. because I can make polyethylene, I could start with this molecule, right? And I can make polyethylene by breaking this bond. Or I could start with this molecule, right? And I can break that bond and make polyethylene. So the monomer unit is arbitrary. Another double bond there. So the monomer unit is like an arbitrary unit in this thing. So you can say, well, my step length, like if I'm going to make this Kuhn chain, my step length LK, well, that's the monomer, but it isn't, because a monomer could be anything. The monomer is whatever you want to say is a monomer. Like if you're a chemist, you can make it from anything. You can start with a whole polymer chain, add another one, and that polymer chain would be the monomer. Right, so it's possible to have a pre-polymer to make polymers. Anyway, so there is though some natural size because you start with a rod. Like the chemical bond is a straight line, right? So the thing is going to have a straight line in it. So what is that length? That's kind of the question. That length's decided by these short range interactions. This is C infinity. One way to say it is if you have NL squared is the chain length, right? And you don't know what the L is, right? So you could say it was a chemical bond. So I could say the number of chemical bonds and the length of the chemical bond squared, right? That would give me a number, R squared question mark, right? So that number would change depending on what. So if I make my bond length twice as long, so it'd be 2LB squared, and the number of bonds would be by 2, then that's a different number to get from that. Right, so there's some problem. Florey realized right off there's a problem with that. So the first thing you can do, there is a number that doesn't change. It's a contour length, NL. Right, that's if you take the chain, it's not squiggly anymore. I just make a straight line, and that's like how long is that line? So that means that the number, if you talk about R squared, it's going to be like NL times L. So NL you replace with L, and then you have this L, unknown L, right? That's going to decide R squared. So if you can measure R squared, and you know the chemical units, and you know the length of the chemical unit, then you can get this L. Right? You can get that, whatever that step length is, just by measuring R squared. Right, so you can also write this. That has to equal also L times L of the bond. So I can take my actual L and divide it by L of the bond. I can call that some number C. That's called the characteristic ratio. That's the characteristic ratio. And it turns out that there's a little problem with that characteristic ratio. Is this problem. So this is a simulation of polymer chains, right? And this is chain index. So I start at 0, I go to 50 or 45, 48 or something. So I have 48 units in the chain. I'm looking at what is this or what is this LP? What's the length of the step? You find out that at the edges of the chain, when it gets to high molecular weight chain, so the bottom is a stiffer chain, the edges of the chain flop around, so they have a shorter step length because they're freer to move around. The ones in the middle are constrained because they have a chain stuck to them. The ones on the end are free to flop around, so they have shorter step length. Right, so this number isn't a fixed number. It depends on them. Like, so you're going to average over that and get the C infinity, right? But so you get this C number, the characteristic ratio, but you want to get the C number is going to change with molecular weight. So you're going to map out C versus molecular weight and find out that it plateaus out. Right, it'll plateau out at some point because the end effect disappears. Because it's going to be, the end effect is always going to be like the number of ends versus the total number is going to be like 2 ends divided by the molecular weight. That's the probability of finding an end.
Can you swap it over?
Oh, yeah, sorry, okay. Here. All right, so the probability to find an end is going to be the number of ends divided by the total number. So you have your chain units, you have one end and another end, there's two ends. And then the number of ends are 2, and then the number of things that are diluting it is m, so it's 2 over m. So if you wanted to say like 1 minus the probability of finding an end, if my molecular weight goes to infinity, that goes to 0, and I just have this c infinity. This would be c infinity times some other number. Something that caused, because it ends, because that LP or L, whatever, versus index has this issue that it's got these end things. So if you let the chain go to infinity, that thing disappears. Right, so then you can get this C infinity, which is what Flory was interested in. Like that's the number you find in the handbooks. It says like, what is the step length of this chain? This is C infinity. Right, so if you know the chemical unit of the chain, and then you can multiply by C infinity, then you can get an actual number, the actual physical number that comes out of the chain. The chain decides that number. The chemist doesn't decide it, the chain decides it. And it can change with the environment. Right? Like if you take the chain and you stick on the side of it sulfonate groups, like polystyrene sulfonate, then they're separated some distance A, then those things will repel each other and that chain will straighten out. And the C infinity will become a larger number. But if you add in salt, so if you add in like sodium, then these charges get screened. So there's something called the device screening length. And if you put more salt in, the device screening length gets smaller. It's a length over which the charges can see each other. So you can get enough salt in that the charges won't see each other, and then it becomes a flexible chain again. If you get rid of the salt, it'll become stiff. So you can kind of tune that step length by kind of messing around with different features in the system. Right? So the question is like, what's the simplest thing you could do? So there's many complicated things you can do. Right? So let's say what's the simplest thing? So the simplest thing is, right, so I'm saying a random walk. So I'm taking this step, I equals 1, I equals 2. And I say, well, and the chain comes along here, right? So say it's in Cartesian coordinates. So then you could have gone here, 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 there, there. And there's this step that's questionable because the chain's already there. So you can't go there. Right, so you say like the average of that step, if you average it random, then that's going to be 0 because it'll go forward, backward, up, down, front, back. They would cancel each other. So it'd come out to 0. But if in the number of these choices is called Z, it's called, could be called the coordination number. Right? It's like how many, so in reality, Z is a big number. In Cartesian, it's 6. Right? So you have, you're going to take that, and then there's going to be the actual. You have our actual, and that's going to be 1 minus Z of those you have. And then the thing that's missing is this Ri, the one in the same direction. So that so when you solve this for what your step is going to be, I plus 1 real is going to be, it's just going to be this, it's going to prefer to go in the missing step direction. So you took out that step, so it's going to go that way. So the missing step direction is going to be the way it goes. But it's not going to be 100%. If it was 100%, then the thing would be fully extended. But it isn't. It's kind of randomized because it's got still 5 other choices to do. So it's those 5 choices that dilute that down. Right, so that becomes a vector like that. So that's like kind of the simplest way to do that. If you want to figure out what R squared is, you do what we did before. So you say that's going to be the double sum of Ri, Rj over I and j. Before we said that Ri is sum of these, right? And those would sum up to R squared, and there's n of them, nr squared. And the other one, it would be random. Like when I doesn't equal j, it's a random. In other words, it could go to any way, so that would be 0. That's how you got the NL squared thing. Right, so, but in this case, you're going to substitute in for I and J this thing. Then you're going to get R squared as the prefactor of that, this same number. And there's still going to be like n of those, but it's going to be, or no, you don't have n. It's going to be a double sum over this 1 minus z to the power I minus j. So if you take one step, and then the next step, you do the same thing twice, the probability multiplies, you get the powers, the number of steps to the power to get that. Right. Then this can be solved. So that's like the simplest, that's like the simplest possible thing. And the reason to look at that is because any complication, so you can say like bond angle, rotation, you can put in the charges, you can put in side groups, anything you want, you can put in. It's going to be the same math. So I'm saying, like, this is my rule. I can substitute that with any rule that goes consequential. So it adds up, like it'll be a power of that rule, whatever that rule is. The rule could be like cosine of theta, then it'll be cosine of the theta to that power, right? So it'd be the same double sum to that power. So you can solve this one, you can solve any constraint that you could think of, right? So you could get somewhat complicated constraints. This is kind of what Florey won the Nobel Prize for. It's also got like confusion to it because another guy invented it, a Russian guy, Wolkenstein, a guy in Russia, and he published it only in Russia and during the Cold War, right? So basically, he won the Nobel Prize. He did a lot of things, but basically won the Nobel Prize for something that he kind of stole. Florey spoke Russian, so he kind of could read the thing before anyone else and published a book on it, right? So anyway, the Russians make a big deal out of that. In fact, because polymers kind of came out during the Cold War, every polymer theory has a Russian equivalent with a different name, named after a Russian scientist. And to some extent, it's true, And some extent, it isn't true. It just depends on which side of the Berlin Wall you were sitting on, I guess. So anyway, this thing can be solved. You find out the end of the story is that it still ends up with being a random walk, NL squared. The only difference is you have this factor that changes it. So all these local things you do, it doesn't change at all your stick figure model, like the idea that it's a stick thing in a random walk. Rubber elasticity, all those things aren't impacted by short range interactions. So the long range impacts it, the short range doesn't. So I'll just go more about this stuff. So Friday I'll go over a paper, and then like Monday I'll go through more of this stuff, kind of more of the details from the Florey book. Right. So hopefully we'll see how this works with recording this thing. And